All of you welcome in our next period. Power series representation of analytic function. Leibniz theorem. Leibniz theorem from advanced calculus. It is in the form of proposition. Let psi with the mapping from AB cross CD to C be continuous function and define the second mapping G from CD to C by G of t, which is the integral from a to b phi of st ds. Then G is continuous. Moreover, if del phi by del t exists and continuous on AB cross CD, then G is continuously differentiable, and G dash of t equal to integration from a to b del phi by del t of st, which is del phi by del t is function of st into ds, equation number 2. Can you see the proof of the proposition? To show that G is differentiable with G dash given by equation 2. G dash is given by this equation 2, which is the integral from a to b del phi by del t, which is function of st into ds. G dash is continuous since del phi by del t exists and continuous. Verify this formula 2. Let epsilon greater than 0 and fix a point t0 in the interval CD. Let del phi by del t is divided by phi 2, and phi 2 must be uniformly continuous on AB cross CD. Implies there exists delta which is positive such that mod of phi 2 of s dash t dash minus phi 2 of st is less than epsilon. In particular, mod of phi 2 of st minus phi 2 of st t0 less than epsilon. Whenever mod of t minus t0 less than delta and s lies between the numbers a and b. Therefore, we have mod of integration t0 to t phi 2 of s tau minus phi 2 of st0 t tau less than or equal to epsilon into t minus t0. Equation number 3. But phi of t equal to phi of st minus t psi 2 of st0 is the primitive. Is the primitive means it is the integral of phi 2 of st minus phi 2 of st0. This is the equation 4. Combining the fundamental theorem of calculus and equation 3. We combine the both. We have mod of phi of st minus phi of st0 minus t minus t0 into phi 2 of st0 less than or equal to epsilon into mod of t minus t0. For MES, when mod of t minus t0 less than delta. Then from definition of G, we have, from the definition of G of t is defined by this equation 1. From this definition, we have G of t minus G of t0 divided by t minus t0 minus integral from a to b phi 2 of st0 ds, which is less than or equal to epsilon into b minus a. Hence, formula 2 is verified and the result of the proposition is proved. Next proposition we see. Next proposition, one can see the theorem. Let f from G to C be generality. And suppose that V bar of AR, which is subset of G of Z, which is R is greater than 0, if gamma of T equal to A plus R e to the power IT, where T lies between 0 and pi, 0 and twice pi, then f of z equal to 1 upon 2 pi I integral over gamma f of w divided by w minus z dw for mod of z minus a less than r. This is the proposition, which is the theorem we have to prove. This is the proof of the proposition. Let Z1 is given by set 1 by R into Z minus A, such that Z belongs to Z, and the function g of Z equal to f of A plus RZ. Let A equal to 0 and R equal to 1. For fixed Z, mod of Z less than 1, we have to show that f of Z equal to 1 upon twice pi I integration over the over gamma f of w divided by w minus z dw. Consider it as equation 1. For w equal to the power is, we have dw. dw derivative of e to the power is, so you know that derivative of e to the power x is e to the power x, therefore e to the power is into derivative of is again with respect to yes, therefore I into ds, and the limits for mod of z less than 1 are s equal to 0 and s equal to twice pi. Therefore equation 1 takes the form f of z equal to 1 upon twice pi I integration 0 to twice pi Total value f of w means e to the power is divided by w minus z, e to the power is minus z into dw. Dw is given by I e to the power is into ds. Here I gets cancelled. Now if you take twice pi in the left hand side, that is by multiply by twice pi, that is, we show that twice pi into f of z equal to integration 0 to twice pi f of is divided by e to the power is minus z into e to the power is ds. Now if we make the right hand side 0, you can write this integral minus this twice pi f of z equal to 0, implies integration from 0 to twice pi f of w equal to e to the power is, not is only, e to the power is therefore f of e to the power is divided by e to the power is minus z into e to the power is ds minus twice pi into f of z equal to 0. Now we can write this twice pi into f of z as the integral of dz. Integration of dz we have z and the limits 0 to twice pi. Therefore we can write this in terms of integration 0 to twice pi f of e to the power is into e to the power is divided by e to the power is minus z ds minus integration 0 to twice pi f of z dz equal to 0. That is why integration of dz by z, and if we put the limits, upper limit twice pi, lower limit 0, twice pi minus 0, we get the previous term 2 pi f of z. Now combine we take the common ds and integration from 0 to twice pi. Therefore integration 0 to twice pi f of e to the power is divided by e to the power is minus z minus f of z dz equal to 0. Applying the Leibniz rule by letting considering that phi of s equal to f of z plus p into e to the power is minus z into e to the power is divided by e to the power is minus z minus f of z. Equation number 2. For t lies between 0 and 1 and s lies between 0 and pi star. well defined and continuously differentiable because mod of z plus t into the power is minus z equal to mod of z into 1 minus t plus t into the power is. This is less than 1. Equation 3. Now I consider g of t is defined by integration from 0 to pi pi phi of st ds. Consider this g of t equal to 0 to pi phi of st ds, which is equation 4. The given proposition can be proved by showing that g of 1 equal to 0, that is to show that g of 0 equal to 0 and g is continuous. Why? To show that from this integration g of 1 equal to 0 and g of 0, that is g of 0 equal to 0 and g is constant function. Stop here.